Reject.
When she says a little bit, she really means about 180 words according to Duolingo. So I love the talk lineup we've had so far. We've covered everything from smart homes to image processing in JavaScript. So naturally, that's going to be the perfect lead-in to sci-fi. Now, just as a caveat, I'm one of those guys who raised their hand during the hacking sleep talk. And right now, I would also like to have heard from him on how you could hack your sinuses. Apparently, there wasn't enough time for me to do that. So you'll have to forgive my stuffy voice. But anyway, you guys came to hear about machine learning. So I'm going to try to give that to you guys. First, a tiny bit about me. So I'm Jonathan Martin. I work at the Big Nerd Ranch with our Rails and front-end development team. I also teach our front-end course. So if you happen to be crossing the Atlantic anytime soon, we teach courses on the West Coast and in Atlanta. We have an awesome place called Historic Benning Mills. You get to go ziplining. It's lots of fun. So you should come out and join us. I love type coercion in JavaScript almost as much as Ruby's scopeless for loops. If you want to make fun of that, though, and you don't appreciate my opinions on that, follow me on Twitter or ping me a request asking me not to talk about that again. So anyway, I kind of lied to you. This talk really isn't going to be about machine learning. It's actually about a very large number with a particular currency attached. Now, I realize that I should have adjusted this slide for the European currency instead. So dollars, just in case you don't know, are the US version of euros, so to speak. So how would you like to build a little round box with a buddy that does nothing but modify the air temperature in your home? You know, that doesn't really seem like a big deal. And how about making it self-regulate throughout the day? Well, apparently Google thought that was a pretty cool idea. In fact, they thought it was a $3.2 billion cool idea. So thermostats that know when to bump the temperature up a degree or two are important, or at least they're important to Google. So for you, that means there might be a potentially a pretty large price tag associated with building something kind of like this. But I lied to you again. This talk isn't about $3.2 billion. It's actually about people, very irrational people. But people is actually a pretty broad demographic, so I'm going to narrow it down to one in particular. Anyone know who this is? I realize the European audience may not be familiar with this beloved actor. So this is Lucy from I Love Lucy. Lucy McGillicuddy, as some of you may fondly know of her. And when she tries to go out to eat, she, being her decisive self, knows exactly where she wants to go, so long as they happen to serve ravioli foo young or chicken chow pizza. Well, she's a little bit less decisive when it comes to picking dinner. So what we'd like to do is help her figure it out and automate her decisions in the future. So we're going to drop this talk. It had something to do with Johnny 5 or image aesthetics or something. I don't know what it had to do with. I've forgotten at this point. Well, anyway, we're going to drop all of that entirely and see if we can code up something to help her figure out what she wants to eat. So we could start with something called a decision tree. So a decision tree branches on whether some attribute or feature, here shown at the top, happens to be true or false. This is the simplest kind of decision tree that we could make. So for example, we could branch on whether Fred happened to order pork chops, for those of you who have seen the video clip, or whether Ethel is going to stick with lamb chops. So those are the sorts of features we could try to branch this tree on. And if we were careful enough and we took enough time, we could build a tree. We could take this generalization and actually build something that would describe her dinner decisions in the future. So instead of having to go through the onerous process of asking everyone to order out so she can make hers, we can instead do this hours before they go out to eat and figure out what she's actually going to order. So that's kind of time-consuming to do from scratch. So this is the kind of thing computers are really good at, because we haven't really captured the entirety of Lucy's decision-making tree. So it would be nice if we could just generalize some sort of program that can build these decision trees based on something that has been seen in the past. In this case, all the times that Lucy has been out to dinner, which for those of you who have watched the I Love Lucy show know is somewhat frequent. So what if we could observe Lucy deciding on dinner several different times and take note of a few things? So every time she goes out to eat, we would just call that an instance. So whether she goes out for ravioli foo young or chicken chow pizza, whatever restaurant she happens to go to, every time that happens, we'll just call that an instance, because in our attempt to get some funding that's approximately $3.2 billion, we just need to throw a lot of terms on it, and that will be helpful. So that would be an instance. But an instance isn't much use without taking notes about the particular things that happened. These are what we would call features. So a feature set is a description of attributes you think are important or relevant to the instance. So in this case, it could be, what did the other people order? Since we know that Lucy tends to make her decision based on what other people at the restaurant ordered. And then finally, we have a label for it. And a label would just be what her end decision was. We happen to know from that short little clip that it's pork chops, but on another night, it might be something else. So the label is just the output we want to predict. We want to predict what Lucy will get, so we will call it the label. And this is, in fact, the canonical machine learning problem, that of classifying, taking a set of instances, learning something about them, and then being able to take some arbitrary instance in the future and predict what its output will be. So given this mapping of instances to labels, how might we build this tree automatically? Well, provided we have a unique feature set for every single instance. So in other words, every time Lucy orders out, if she has the exact same features for that evening, she should order the same thing. Now, given it's Lucy, there are some other random attributes that might affect what she would like to get for the evening, so that may not be the case. But let's assume that given what everyone else orders, she will always order the exact same thing if they make the same decisions. Well, in that case, it's fairly easy to come up with an algorithm that builds one of these decision trees that exactly matches every single one of the times she's gone out to eat. So if we observed her 5 times making some decisions, we could build a decision tree that will exactly capture that sort of information. But is that exactly what we want? In the future, she might make a decision that we have not seen before. So what we'd really like to do is take her decisions and see if there's any sort of pattern in them. In other words, we want to generalize what her current decisions are so we can figure out what a future decision will be. Well, there's a synonym for generalize. It's called simplify. So what we would like to do is generate a tree that is simple, and we'll make the assumption, we might arbitrarily decide to call it Occam's razor for some reason unbeknownst to me. Well, we might say that any solution which is simpler, for some arbitrary definition of simpler, will be more useful in the future. Or in other words, it doesn't give us much to arbitrarily make more complex things just because they could be more complex. We tend to pick the easiest or the simplest solution in science. We should do the same thing in our little algorithm. So how could we do this? How could we actually automate this sort of thing? Well, we could try a divide and conquer approach. So what we should try to do is take the set of instances and try to divide it in half by picking one feature from the feature set, which splits the current instance set in 2. So ideally, what this would mean is that there's one feature that if we split on whether it was true or false, we would exactly cut the instance space in half. And ideally, if you keep doing this, you'll get a nice little binary tree, and you have a very nice short tree that's only big O log base 2 of n. So a very short tree is what we would like. That would be what we consider a not so complex tree. So there's some ways we could try to do this. There are some heuristics we could use to try to figure out how we should split on the tree. A really popular one, though, is info gain. So with info gain, what we want to do is try to find a way to cut that instance space in half. Or in other words, if we were going back to the Lucy analogy, we would want to take all of the instances and find some attribute. Say it's that Fred happens to order something, and we want to find out which of these attributes splits her decisions in the future in half. Well, in that case, what we would do is we would make that the very next node in the tree. So revisiting the tree diagram, that would perhaps be our top node. And from there, we would just continue going down the tree, picking the next available feature that has not yet been split on, and figure out which one does the best job at splitting the instances in half. So there's another word for this. So it's called entropy. What we want to do is entropy is a measure of randomness. So the higher the entropy, that means the data is more random. It's harder to predict what its output will be. So low entropy is the exact reverse. It's less random. At the extreme, an entropy of 0 means that it's completely deterministic or constant. So what we want to do is find which of these attributes most reduces the entropy of the 2 subsets of instances. So in other words, if we found that one of Fred's decisions happened to split Lucy's final decision into 2 groups, maybe it was lamb chops or pork chops, that would be reducing entropy down to 0. That is our end goal, is to be able to make a probabilistically correct prediction. So this sort of algorithm, InfoGain, is a little bit heady, but it's almost intuitive. But it's not always, as we'll see, going to be the best representation for data. But it's a fairly simple structure. Keep that word simple in mind. So now we finally have an idea of how we're going to build this tree automatically. So now we have to figure out how we're actually going to train it. So ideally, we have a bunch of examples of when Lucy's gone out for dinner. So what we'd like to do is we'd like to take all of those instances to train this tree. So ideally, we have this little InfoGain algorithm running. We have a mapping of all these instances that Lucy's gone out to eat and what she actually ordered. So what we'd like to do then is tell it to train on all of those examples. And we could do that. But what we'd get back is a tree that exactly matches all of those instances or exactly predicts it. That means we'll probably be getting a fairly complex tree and one that may not generalize very well. So there's maybe a better idea. Maybe we should take just some of the data. Say we take 5 instances of Lucy going out to dinner, and then we train the algorithm with those. And then we reserve the remaining ones just to test. So a very common split for this sort of thing is to have 90% training and 10% testing data. There's also validation for those of you who are interested in actually applying this and getting some better results with cross-validation. But if we take training and testing data, that's already a pretty good split. We'll take 90% of the data, or say it's just 5 instances of Lucy ordering out, and use that to train up this decision. And then we'll run the test data through the net and compute how accurate it was at figuring out these other decisions. If it's fairly good, that means we probably developed a decision tree that's fairly generalized, which is what we want. We want to be able to use this to figure out what Lucy's decisions will be in the future. Now, honestly, that's not really incredibly interesting. Decision trees are fairly simple. You can whiteboard them, which should say a lot. And they're really not going to be that impressive in our quest for funding from Y Combinator, for those of you who happen to follow the news regarding Thalmic's funding. So we really need to come up with an algorithm that sounds a little bit more organic. That seems to be the trend nowadays. So maybe we could try to come up with an algorithm or data structure that's maybe loosely based on the human brain. So after wrestling with a bunch of names late at night while you were trying to adjust to this current time zone, you naturally decide on using neurons somewhere in the name. Now, neurons aren't much use, as you know, on their own in the brain. You need networks of them, all connected through synapses. So naturally, you settle on the name neuron networks. Well, except the adjective form sounds a little bit more interesting than that, so you go with neural networks. But then your advisor tells you that your investors will think this has something to do with brain matter, so you're required to call it artificial neural networks. Great, so in the span of about 2 minutes, we've come up with our own algorithm. Sounds pretty sweet. We've probably got some funding on the way. So let's take a look at how we might make use of these neural networks. So we arbitrarily decide that every one of these neurons can have some inputs, and it has one output. And it has a sort of feed-forward style, which means we pass data into one node, it outputs some value, and that gets fed into another node. Hence the term neuron network, or neural network. Now, the only thing is we have to figure out how we take those inputs and map them to a single output. Well, what we could do is we could weight the different inputs. For example, we might want to say that the feature F3 has less influence over the output than F1. So at first, this just kind of looks like a linear sum. You're just doing a weighted average of all these features. But then we have a special function on the inside called the activation function. And that's a fancy term. It really just means any nonlinear, monotonically increasing function, for those of you who happen to remember that back from the dark ages. In reality, that could just mean it's a square wave or a hyperbolic tangent. So what we would do is we would take this weighted average and plug it into that activation function, and the end result would be our output. Now, we should all be questioning, why do we just complicate matters? Why couldn't we have just gone with a nice little weighted sum? Since we're trying to invent an algorithm, we want it to be simple for our sakes, just have some cool terms for the people who want to invest. Well, the activation function is handy if it's nonlinear. So here's a typical activation function that we would use in these perceptrons. For example, this is the hyperbolic tangent. Notice that it is monotonically increasing, which just means it never decreases. And it's nonlinear, so it's not straight. So if this was straight, say it was just a regular line, y equals x, Well, in that case, that would just be a multiplier on our weighted average, which would basically reduce our entire awesome neural network down to a single linear sum. That would not be very interesting for the sake of our investors. So instead, we put nonlinear activation functions in here. And it turns out that if we use particular functions, we can actually do a really good job at mimicking any function. So for those of you that remember what a little bit we talked about in functions back in the days of algebra, functions are mapping from some input to some output, which sounds exactly like what machine learning or being able to do any of this sounds like. We're mapping from some instance, say of Lucy and what she orders, to some output. So all we had to figure out was some clever representation that would allow us to build these functions. Well, now we have to move on to the next part. We have to actually figure out how to train this. So there are actually several different strategies to training a neural network. And the training process just basically means we have to figure out what the weights are on all these different perceptrons. So what we could do is we could just start with some random weights on all these perceptron inputs. So revisiting the perceptron, we would initialize W1, W2, and W3 to some random value. Now, that doesn't seem like much use, so what we could do is we could take our training data, say it's Lucy ordering out, and pass it through the network and see what its overall prediction will be. Then we could calculate the difference between what it should have been and what that network actually outputted. Once we know that difference, there are actually some cheap ways we can figure out this gradient. So for those of you who remember calculus whenever we talked about gradients, gradients would just tell us essentially the slope of this function relative to the input and relative to the weights. So in other words, we could try to figure out how changing these weights slightly gets us closer to what we actually want, because with the training data, we have both the input and the output available to us. So in that case, we could just move in the direction that reduces the error, or in other words, gets us closer to the desired output. Well, that's fairly simple, and there are some constants there are some rates that we can actually use that help us move in the correct direction. So this technique is called gradient descent. Now, sometimes gradient descent, if you think about it in terms of hills, if you were looking for the peak or looking for a trough in a bunch of hills in your neighborhood, you could go to the first trough you see, and you know that it's a trough because you have to start climbing uphill again. But it could be that a mile down the road, there's a trough that's lower than the one you're already in. And if your goal was to find the lowest trough, you might never find it if you didn't do some more exploration. So this would be called a local minima. Well, we don't want to get stuck in local minima. Ideally, we want to find some weights for our neural network that do the best job predicting the current decision. Well, in that case, we can actually do a little bit of random exploration. So we add another fancy term on it for our investors' sake. We call it stochastic gradient descent. So there's a bunch of these different techniques, but they all come down to figuring out what weights produce the best classifier for your given domain. Now, neural networks are definitely a lot headier than decision trees. Now, they're headier both to build and to train. But they are better able to represent these arbitrary functions, which is also a downside. So whenever an algorithm can represent a larger domain of classifications, it takes much longer to build an optimal classifier. This trade-off between simplicity and representational power is so important, we should probably give it another name, since this is becoming such an important aspect of the funding process. We call it the no free lunch theorem, coincidentally. So now we've laid down a ton of terminology. We've explored two different ways we could build things that could actually figure out some future decision based on currently seen data. Now, as we've seen, decision trees are a little bit easier, while neural networks possibly have a little bit more power. So let's move on to the actual punchline of this talk, because I lied to you again. I didn't actually lie to you that we wouldn't get to image aesthetics. So image aesthetics is kind of an interesting domain, because we're dealing with a lot of data, we're dealing with a lot of pixels, and we're dealing with something very abstract. It's sort of easy to start out with, say, Lucy's dinner decisions, which is a fairly small data set, and to figure out how we might do some predictions. It's also very easy to hard code it. So for example, if you had seen 10 instances of Lucy ordering out, you could build your own program that outputs the decision and probably do it very well. But if you want to figure out what images will make very good images or how a human would rate it, it's much harder to come up with 10 lines of code that will describe it. So at this point, we kind of need we need a way that a computer can take the ways humans have classified it and builds essentially a little program that can actually figure it out for us in the future on new images. So the first question we should ask is, what is our data set? Well, when we're talking about aesthetics, it's probably related to images, and in fact, that is going to be our data set. But the second most important question is, what will the features be? So in the case of Lucy's decisions, we said that a feature might be what everyone else ordered. Well, in this case, we're dealing with images, so naturally, we might make every single pixel in the image a feature. Now, those of you who have maybe done a tiny bit of machine learning might think this is completely futile, but it turns out there are actually some really good applications for this. As we'll see when we get into JavaScript world, there are actually some really good demos out there that take every single pixel in an image and can train it. Neural networks are very powerful because as you start adding more and more nodes, the nodes naturally start to represent different things that show up in the image. So for example, if you were trying to process what was in an image, for example, say it was a particular animal, and you wanted to come up with an algorithm that could take a picture and figure out what the animal was, you might start finding that these different layers of neurons and perceptrons are actually representing these intermediate areas. So in other words, converting pixels to some more abstract idea. Now, in reality, it's never quite that clean. It's rare that you can go into a giant neural network and figure out, oh, it's figuring out that it's converting this image into a thing, which is converted into an animal, which is converted into a mammal. That's highly unlikely, but there are some cases where this sort of thing does happen. So what we'd like to do is we'd like to use all these pixels. That'd be kind of nice. But that would take an eternity to train, by which time Y Combinator would no longer be interested in you and might move on to the next company. So in that case, we need to cut down on the number of steps here. What if we could help the neural network by actually giving it some features that get rid of the intermediate steps it would be figuring out? So for example, what if we could figure out some particular attributes of a good image that make it good, that are strongly correlated with its goodness, as it were? Well, we can do that. There are actually some really good rules in photography that might be somewhat correlated. So the first one that many of you have probably already seen if you use your iPhone and you use the composition mode. A good image typically places the points of interest on a rule of thirds grid. Now, this is actually an approximation. It's technically the golden ratio. Basically, everything in photography, everything in math, if the golden ratio is not involved, it's not that interesting. But the rule of thirds is close enough for our purposes. And essentially, we just don't want the main points of interest or the subject too close to the edge or too close to the middle. So those of you who have put up your avatars, I've probably seen all of them and probably mocked them because they're all exactly on center with a little too much space above the head. So if you want to improve it, go try the rule of thirds. So that's the first thing we could use to somehow figure out that an image is good. Now, our first question should be, how on earth are we going to take this image and figure out where the points of interest are? Well, there are some ways. They're fairly complex, but what we could try to do is break down the image and find areas with a lot of contrast. And then we would know that, oh, there's a big blob here. That blob kind of looks like it's on the rule of thirds line, so maybe this is pretty good. So it turns out there are actually some deterministic methods you could use. It's not just all hand-wavy. Now, another technique that's kind of related is loneliness. So good photos typically emphasize only one or two subjects. So in this image, for example, even though there's a lot of detail here in the water and in the sky, your eye immediately is drawn to the boat. Why? Well, because it stands out from everything else on its own. So we would call this loneliness. Now, there's another example of this. If you happen to be looking at a picture of a beach, and the beach is very smooth, and there's just one person standing in the middle of it, that would also be an example of loneliness. Now, the interesting thing about loneliness is that it's much harder for a computer to figure out, because we naturally would see the human in the picture and say, ah, that is important, that is the subject. Whereas a computer might say, oh, that's only a few pixels, it's not even that large. So loneliness is much harder to figure out. But for the most part, we can still approximate it pretty well. Now, strongly correlated with loneliness is simplicity. So simplicity is strongly related to it, but it emphasizes overall detail instead of strictly enforcing one subject. In other words, it starts looking at a much finer level and says, how much detail, how much noise, or how much texture is there in the different parts of the image? So in this picture, for example, The background is fairly simple. It's very smooth because we've got the shallow depth of field, and it doesn't have a lot of noise. Whereas the cat on the side has a lot of detail and a lot of lines and edges. So simplicity would say that there should be a contrast between the shallow depth of field and the main subject. Now, again, this seems a little bit hand-wavy, but it is actually fairly easy to compute which areas of the image are very simple. So, for example, the background is obviously very simple, it's very smooth, and then the subject is not as smooth. So we would say that the overall image is maybe 2/3 simple. And then finally, with contrast, we want to somehow juxtapose the different levels of light in an image. So this is really important in black and white photography. So in black and white photography, you don't have lush colors to help cover up poor contrast and luminosity. So for example, when you go looking through your photos and you're trying to figure out which ones have the best composition, it's often very helpful to flip to black and white, just to see how much contrast there is in the image. So with a black and white image, that's very obvious. With a color image, it's a little bit harder. But essentially, we want to have really strong changes in the luminosity that's shown. Very often, these are the little thumbnail pictures that capture attention when you're on Flickr or some photo sharing site. Because if you have a thumbnail and there's not much contrast, you're not really able to see much of the detail. Well, when it's blown up, the same thing sort of applies. So we want an image with a lot of contrast, and this is actually fairly easy to compute. There are some different methods that'll help us. And then one last one that we could explore is color theory. So for those of you who did some sort of design course, you might have learned about complements or having warms and cools in an image. So in this image, for example, we see that there's a really strong contrast in the colors. There's green, there's blues, there's purples and yellows, but there's consistently a contrast of the warms and the cools. You have cools on the mountainscape and you have warms in the sky and on the mountainside. And it turns out colors like blue, green, and orange tend to go really well together, whereas red and some slightly off version of red might not go as well together. So color theory, again, is a little bit mushy, but we can actually put some hard constraints on it and come up with some numerical value that says how good the color theory is in a particular image. Now, one of the reasons I could wave my hands a lot for these sections is that we actually can process the image into, say, 16 or 64 little squares. And then on each of those little squares, we could compute how smooth is it, how much contrast is there. Now, very often, we'll actually do a transform. It's called the wavelet transform. It's sort of like frequency analysis for an image, although that's very hand-wavy. Don't hold me to it, technically. So wavelets are useful because they help decorrelate one local section of an image from the rest of the image. So for example, if you had 16 squares and you were trying to figure out how smooth the part on the top left was, you probably wouldn't want it to be correlated with the other ones. And this becomes more important when you start looking at things like simplicity and loneliness. So wavelets just help us detangle little parts of the image from each other. So a lot of the features that I already introduced actually use wavelets as part of their implementation. So it's certainly no picnic to compute all of these different features. And in fact, you could use it as a research paper, and you could spend years trying to come up with these. Now, obviously, this is a 20-something minute talk, and I'm already almost over time, so we don't have time to go through all of those. But there are some established techniques that let us turn these vague rules of thumb into some numerical value. So ideally, once we have these values, we should be able to train a neural network of some sort. So we could do this, right? We could do this for Facebook or Flickr, perhaps, and make $3.2 billion. Unfortunately, we're a little bit late to the game. Someone has already done this, and there are actually quite a few research papers out there on image aesthetics. It seems a little bit strange for people to be devoting so much of their computer science career to doing this sort of thing, but it's a very interesting problem. So there's a paper, actually, that came out of Pennsylvania State University. It was put together, and it explores a bunch of these different types of feature extraction, and then it had a total of 56 of these. So that's a lot of features, but it's very useful that we can actually train on these. Now, I'm a little bit short on time, so I'm going to go ahead and kick out of here, and we'll leave Lucy to make her dinner decisions a little bit later. But it's pretty neat that we were able to go from decision trees and talking about dinner decisions to image aesthetics. The algorithm that I showed you guys, or rather the paper referenced there, by the way, got around 70% accuracy on some data sets, That's incredible, that we can even do those sorts of predictions. And you have JavaScript libraries to help you out with this sort of thing. There's 2 libraries I'm just going to mention. Brain.js is a very popular one. It's a very low-level one, I might add. It has a very cool demo on contrast. So for those of you who are trying to figure out if text planted on an image shows up very well, they actually trained it with machine learning. And it's very easy to use. Once you require it, you just pass in an array of input to output objects, and then you run it on your example. In fact, sometimes it's a little bit too simple. So if you need something more powerful and you're ready to dive into the internals of neural networks, check out convnet.js. Convnet.js, just from the number of lines of code, you can tell is much more powerful. It lets you specify activation functions, for example, and it lets you run it on one training instance at a time. The end result of running any of these, whether it's on your server, say it's Node.js, or on the front end, is just some set of weights for your neural network, which describe that domain very well. So as we've seen, neural networks can be very powerful, but machine learning in general is an art that you can apply in many different arenas. So you could use it for your image aesthetics, you could use it to figure out how to improve user data, or you could just use it to help you figure out what to get Lucy for dinner. And that's all. If you guys have any questions or comments, let me know. I'm at Nibbler.
Reject.